I'm super excited to be here virtually. Unfortunately, we can't be there. Kareem and I can't be there in person. I hope you're all having a great time. And we're here, Kareem and I are here to talk about, to give a roadmap update on FVM. First, I'm just gonna advance my screen. Okay, cool. So this is the agenda for today. We've got 30 minutes on the clock. We'll try to be quick. We have a ton of material to talk about. First of all, I'm gonna cover M1 and what is this big milestone that is going to be shipping to the network literally in less than 48 hours. And I want to do a quick recap of everything that has gone through, that has gone in this milestone. I don't think we've communicated the amount and the magnitude of work that has gone into this milestone. So I really want to take this opportunity to emphasize everything that has happened in M1 and why it's so crucial and so important for this milestone to go live into the network ahead of activating user programmability, and also, you know, to acknowledge the work of so many people that has gone into M1. This is really one of the critical milestones that installs the FVM technology on the network. So I'll talk a little bit more about that. Then I'll give a roadmap update about M2 and the different tracks comprehended there. Then I'll talk a little bit about some of the key protocol designs so that people can form kind of like a mental idea of what's actually going into M2 and what are the different protocol changes that they can expect here. And then I'll hand it off to Kareem. He's going to talk through the EVM runtime architecture. So sneak peek here, M2.1 is going to be EVM compatibility, and I'll talk about that a little bit later. Kareem is going to give us an update on what the current model for the EVM runtime architecture is, and also he's actually been working on a prototype. Most of the bulk work has been done by him, and he's going to give an awesome rundown and a demo on that. And then we'll jump into conclusions, and if we have time, we'll do a quick session of questions and answers. All right, so just to refresh everybody, what is the FVM project? The FVM project brings on-chain user programmability to the Filecoin network. And the key of this technology is that it allows users to deploy new primitives to the network that are leveraging the unique characteristics of the Filecoin network itself. So obviously features like provable storage, retrieval, what is the health of a particular piece of data, what is the status of this particular miner, and stuff like that to build use cases like, for example, decentralized compute, data DAOs, L2 networks that anchor onto the Filecoin network, perpetual storage, replication workers, repair workers, retrieval markets, and a ton more. So the FVM is really this. We think that the FVM is this crucial piece that is missing in the Filecoin vision, and this is what we're aiming to ship with this project. So it's all about kind of like what I like to call programmable storage primitives. And the ability really, I think it introduces a paradigm shift in the sense that I don't think computing has yet seen a system that allows us to treat storage as something that can be created, programmed, brokered, and incentivized in different forms. So I think that's one of the key things that the FVM project introduces and the vision behind this project. Now, the FVM roadmap, it's on the website. I'm just gonna kind of like refresh it a little bit. It's gone through several phases. This is a complex project. Take into account that the FVM is really changing the engine of an aircraft while it's in flight. And it's really, really that. So we wanted to do this with a lot of care and do it in phases. So FVM milestone 0 was all about canary testing the FVM against mainnet and kind of like conducting those initial prototypes, validating our initial designs around WASM, around IPLD interactions, and a bunch of other things by testing and targeting mainnet and validating the mainnet blockchain. Now, FVM M1, which is the milestone that we're shipping in 2 days, in less than 2 days to the network, really installs the core of the FVM technology on the network and does a massive, massive lift and change here because it migrates the core of the business logic and the built-in in the network, which is provided by actors, and these particular actors we call built-in actors, migrates those to an entirely new runtime. The deployment format is different. It's was and bytecode. The code bases are different. We've migrated from specs actors, which was written in Go, which was the reference implementation, into a Rust implementation, which was initially contributed by the Forest team. So it's really this key milestone that introduces the technology and installs the technology in the network. Now, M2 is the one that I want to spend some time talking about as well. And that's where we are right now. So the team, the FVM core team, has already shifted gears, and we're already working on M2. And it introduces user programmability in 2 core tracks. This is the EVM track and the native track. And finally, there's going to be a set. After M2, we'll go into a more incremental delivery mode, where we'll have further protocol upgrades and features and runtime features and so on contributed in future milestones. Now, this is the big celebratory moment. Many months of work have gone into this. The epoch for the SCR upgrade, which is the name of the upgrade that is introducing milestone 1 of the FVM, network version 16, has been set. It's in less than 48 hours. And as I said, this installs the WASM-based FVM to the network and migrates the built-in actors. So I can't hear you guys, but please a round of applause for all the amazing people. And it's a team. It's many teams across many time zones, across many cultures, across different walks of life, like literally in different organizations, literally contributing to this. So it's been a massive lift, and we're very excited about this milestone. Now, I wanted to kind of like touch on what's happened behind the scenes here and what's happening with M1. First of all, as I said, it's a massive change. It's around 100,000 lines of code that are changing in critical production code. This is literally the execution pathways of the network and the business logic that is powering the Filecoin network. So it's new execution paths, completely new actors, completely new bundling code, the way that actors are deployed in the network, reworked gas model, and a ton of repos affected by these changes. So ref FVM, it's a new repo. Built-in actors is a new repo based on forest actors that we used as a base for that. The FVM specs, of course, Filecoin FFI received a massive facelift and a huge refactor. Lotus and also 3 client teams contributed actively to the development of this milestone: Lotus, Forest, and Vina. So thanks a lot to everybody that made this possible. Now, just to talk about a little bit of the technicals of the changes that are going in, I'm gonna all of the changes that are going into the FVM to FVM M1 are actually specified in FIPS and Filecoin improvement proposals. So you can read all about them in the FIPS repo, but I just wanted to spotlight each one of them so that people understand all of the work that has gone into also specifying these changes in an open manner so that the community can vote on them and kind of like, get to consensus that this is something that we want to ship. So FIP 30 was the baseline technical spec for the FVM. And this is the spec that is ultimately going to keep getting updated as we introduce new features and as we introduce new syscalls and architectural changes, and we make changes to the memory model and a bunch of other things. So this really captures the architecture, the container contract. So when you write an actor, what is it that you can expect from the environment, and how you can access those features that the environment provides to you to pre-restate, to make mutations, to do a bunch of other things. The extern, so this is the contract of the FVM with the client and the memory model and a bunch of other things. Of course, this is all on the FIPS repo. So if you want to take a look and do a deep dive into this, feel free to go and open this doc. Then the FIP that actually, so FIP 30 introduced the baseline spec for the technology, and FIP 31 is the one that proposed the activation of that technology by performing a migration in mainnet. So this specified the upgrade procedure. It migrated from synthetic code CID. So this is for people who operate nodes and so on. And are familiar with chain explorers and so on. You'll recognize the FIL/7/verified registry or miner or whatever, right? Storage miner. These are the code CIDs, how we used to refer to the code behind actors before there was actually a portable way execution format for defining the logic of those actors. So because there was no portable execution format, we had to invent code CIDs, and these were not content addressed, right? These were the key content. CIDs means content addressed, content identifiers, right? And it's implicit in the word, it's content addressed. These were not content addressed. So for the first time ever, we're actually deploying code that is content addressed. And Filecoin is very unique in compared to other blockchains in the sense that it separates the actor and the smart contract, so to speak, from the code that is backing that smart contract. And this gives us very nice functional features that I might cover in this presentation or that you learn about in future presentations. Now, this also specified a test plan and a testnet schedule. Now, FIP32 is, so given that we have this new runtime environment that has completely different execution characteristics, and also we have this new bytecode that is specifying the execution logic, and that we know that all nodes are going to follow, this introduced a bunch of gas model updates to account for all of those changes in the network. So things like execution gas, syscall gas, extern gas, and changes to some of the fees. Now, a lot of testing went into this release. As I said, it's a massive change for the network, a massive technological shift. And I'm just talking about some of them here. There were more. So things like test vectors played a big part in validating the correctness of the execution. Built-in actors, when we inherited or we used the forest actors for as the new built-in actors for the network, we had to extend the testing that they were tested with, so the testing coverage, so to make it even with specs actors and even improve it. So this is the previous code base. Then we also had an integration test framework contributed by Polyphene, which is a group that is working in the FVM environment, and we love the work that they do. So shout out to them. And this was a key contribution because it allowed us to simulate special conditions that were otherwise impossible to simulate with test vectors. And this allowed us to kind of like do more and further correctness testing and robustness testing. And then we also, during a very long time, we performed canary testing against mainnet. So this is basically running the FVM, validating mainnet, even though mainnet was not executed by the FVM. So that's why we call it canary testing. Now, there was a ton of hardening and audits as well. So the team got together, and after kind of like we had finished the bulk of the engineering work, we brainstormed about everything that we wanted to vet very, very, very closely to make sure that we did things right. We had an external audit by Alex Wade. We had internal audits. We had crowdsourced audits as well on Immunify and Gitcoin. And yeah, that was very fun. A ton of work. Also, during this time, we've been working with early builders who have been building on a special branch of the FVM that allows them to deploy native code or WASM actors to the chain and local networks. So things like the FVM actor playground, which is built on Observable, has come from Jim Pig. Jim just decided to hop on and just started building a bunch of things around it. And he has a very kind of like didactic form, and he likes to create observable notebooks for things. So it's a very nice, putting it together, it's a very nice walkthrough flow of how an actor works and so on. And this allows you to basically hack on small snippets of actor code and deploy them to a local network and test them without having to spin up a node yourself. So this is very cool. Now we've got our friends at Sondax who are developing an assembly script SDK for native actors. We've got Rust SDK macros by White Label. We've got a TinyGo SDK as well, which IPFS Force is working on, and a ton of more things. We need to do a better job of publishing everything that's happening in early builders. There's a ton of things happening. And one of the things that we want to do is create a community showcase section in the FVM website. And I think that's probably going to come in the next weeks. So now this is all about M1. Now I want to talk about M2, the milestone that enables user programmability. And this is probably the one that most people are excited about, even though M1 introduced the bulk of the changes here. So there are two tracks to M2. There is M2.1, which is the EVM runtime, and there is M2.2, which is the WASM, which we've been calling the native runtime as well. Now, the EVM runtime, if you look at the website today, these are flipped. We've made kind of like a decision based on community input and signals that were received at talks, conferences, and so on, that really what people looking at Filecoin from the outside are expecting of Filecoin is really to be able to take all of that kind of like backpack of knowledge that they've accumulated by building smart contracts for Ethereum and Solidity and so on, and using all that excellent tooling that already exists in that community, Hardhat, Remix, MetaMask, and so on, and just applying it to Filecoin. And we listen loud and clear, and that's why we kind of like reprioritized things a little bit here, and we decided to ship the EVM runtime as the first programmable runtime for the Filecoin network. Now, this also allows us to onboard a massive set of bulletproof, well, nothing is bulletproof, right? But production grade audited smart contracts like ERC20s, NFTs, and so on that have been battle tested for many years. So this allows us to kind of like onboard all of those contracts quickly to the Filecoin network. Now we know that the EVM runtime is not going to be the most performant runtime because it is in some form emulated. So that's why in parallel we're going to continue working on the WASM runtime. Now this one has a longer timeline because we need to build new tools to match the developer experience that people are expecting of blockchains these days. But the trade-off here is that it will give us better performance when it comes to executing these actors because they're closer to the WASM bytecode itself. And also the benefit is that if you not already familiar with Solidity, or you kind of like want to change programming languages a little bit and want to explore something new like Rust, AssemblyScript, or even Go with TinyGo, you'll be able to write actors in your own language. And the nice thing here is that you can use your existing tooling, the IDE. However, all of the tooling to actually deploy, test, debug, and so on, this is something that we need to develop. So that's why I say this has a longer timeline. And we're working on these threads by engaging the early builders community, who are completely focused. The current cohort is completely focused on the WASM runtime, and they continue creating tooling. And if you look at the Filecoin projects /dev grants repo, you'll see a bunch of dev grants that we're giving, all related to native programmability. Now, one thing that I do want to note is that the user programmability M2 as a whole is likely going to be preceded by another network upgrade. So this means that between now and M2, there's probably going to be another network upgrade, network version 17, which is going to introduce programmability enhancements to the built-in actors, so that when folks go and deploy things, they are able to use all of the Filecoin features. Now, the features in the built-in actors, they're able to use things like provability and data tracing and a bunch of other things, so that their actors are truly useful. Now, one thing as well is that part of the EVM runtime, or M2.1, is the ability to access Filecoin features from Solidity. So these are not like dissociated environments or kind of like actor environments. They are from EVM actors. You should be able to access the full catalog of features that the built-in actors are exposing. So they'll be on parity with everything else that will be deployed on the network. Now, all of the M2.1 work started with an initial parent spec for EVM that defined the FVM to EVM mapping. You've got a link there. It's in the FVM specs repo. So if you want to track, and there's a ton of specification work going on right now. So if you want to track that, then I suggest that you subscribe to the FVM specs repo and also to the FIPS repo. We're kind of like tend to incubate these specs in the FVM repo. And then eventually, once they're more solid, we move them to a FIP. Now, there's a there's a runtime prototype that we've been working on, and especially Kareem, and he's actually going to be demoing it in a few minutes. And we're kind of like approach M2 from two different directions. We approached it from a spec first direction and from a prototype first direction, because we know that there are a ton of uncertainties that will only be uncovered if we actually get hands-on and start producing a prototype, and we start like digging into those particular areas that have hidden gotchas in them, right? So this is the way that we decided to approach M2. And the idea is that specs and prototypes are constantly feeding each other, and they'll meet in the middle. So as of today, this prototype is able to deploy EVM bytecode onto the Filecoin network. And it's able to run a simple coin contract that performs states, reads, and writes. What Kareem is going to show is actually a little bit later is actually an integration test. So it will be easier to follow. Now, I wanted to talk through, just give you very brief touches on some of the key technical designs that are going into M2.1. And I'm going to talk through 5 or 6 of them just very, very briefly. So key design number 1 is account abstraction. Account abstraction basically moves the message validation logic inside actor code if the actor wants it. So you'll be able eventually to deploy an actor that is able to validate, that is able to act as a sender by validating messages directly inside actor code. This is critical for us and for EVM, for Ethereum compatibility, because it allows us to keep the protocol, the Filecoin protocol, decoupled from the Ethereum message format and the signature validation. This allows us to basically not tangle both protocols and the fate of both protocols, because both the Filecoin network and the Ethereum network are going to continue evolving. And if we had this coupling at the base layer, it would get messy in the future. So this allows us to move and offload this validation logic into an actor. So we expect to introduce an actor, a new kind of actor that account actors will be able to upgrade to. So if you have an F1 address on Filecoin, this is a SecP 256K1 key, you'd be able to transition that to an Ethereum compatible account. And now that account would be able to validate RLP encoded messages carrying Ethereum signatures that have been produced from wallets like MetaMask. So this gives us native compatibility with existing wallets in the way that they sign transactions. Now, there's a lot. There's a lot to this. I know I made it sound like a little bit simple, but there's a lot to this. So if you're interested in seeing this discussion develop, then I've posted two links there in FVM specs and FIPS. Now, another key thing is creating a universal address space. Problem is that Ethereum has a single 20-byte address space, which contrasted to Filecoin. Filecoin has several address types, which have different lengths. So our solution is to create a universal stable address class that will enable addressing that will enable the EVM smart contracts to address Filecoin actors. Another key design here is the undifferentiated actor. So in Filecoin, you can't send funds to an existing address, unless they're an account, unless they're a pub key address. So basically, if you do that, you'll be creating the account actor then and then in that send. Now, the problem is that when you send from a smart contract to a universal address, you don't know if that's going to be an account or if it's going to be a contract down the line. So the undifferentiated actor is going to act as a placeholder, which will then be able to the property of that address will be able to be claimed by presenting the first signed transaction, if it turns out to be an account actor, or by deploying a contract whose deployment address resolves to exactly that address. Now, some of the key designs here, I won't go too much into these logs and events. We don't have this feature. Short headline here is Filecoin doesn't have this feature. We need to introduce something like that. It's not going to be the same design as Ethereum. We're generalizing the design to something called execution artifacts. So in the future, so basically transactions will be able to post artifacts from their execution, like logs, But in the future, they could post things like callbacks, or they could post things like promises, or they could post cross-chain calls, or things like that, which have a lot more utility going forward. Things like, another key design here is Solidity interactions with built-in actors. So we need to make it easy and simple for Solidity code to be able to address built-in actors so that they can leverage Filecoin features. Now I'm going to hand it off to Karim. He's going to do a quick runtime. He's going to talk about the EVM runtime architecture, and he's going to do a quick demo as well. Karim, do you want me to keep sharing my screen, or?
I'll share my screen because I'll also, yeah.
Awesome. All right.
All right. So thanks, Raul. First, let me talk about what is an EVM native actor. An EVM native actor instance essentially consists of two things. It's a code CID that's WASM bytecode, can be reused across any actor instances, and an IPLD state root. It's bound to a specific instance and stores actor state. EVM actors interact with the rest of the world, including their own state, by invoking FVM syscalls that are exposed through a well-defined EBI surface. EVM actors are invoked by off-chain messages, and the logic from the bytecode mutates the IPLD state by replacing its own state root, and may optionally return an output. So when you couple a link to the WASM bytecode with a link to an IPLD state root, together you get a native actor that has its own separate address and its own living object. And the EVM actor is implemented in terms of a native actor. So EVM contracts are essentially instances of native actors that point to WASM bytecode. Their WASM code CID implements an EVM runtime, has the EVM stack machine, the EVM codes, handling, and all that sort of stuff. They have a link to an IPLD state root that stores the contract's bytecode and the current state of that contract. Once an EVM contract is instantiated, the bytecode is immutable, but the state mutates as a result of running the bytecode when it's invoked by transactions. EVM contracts invoke the FVM runtime to access EVM functionality, including within its own state. And also, an EVM actor instance has a Filecoin address and an EVM address, so it can be invoked by other EVM actors and by native actors. We're working, like Raul mentioned, on having a universal addressing, so we might end up having a way of seamlessly transitioning between those two, but this is still being designed right now. So let me talk about how an EVM contract deployment works. EVM contracts are deployed by sending a transaction to address 0 with the init code. It sets up the initial state of the contract and returns the contract bytecode. So here on the left, we have an RLP Ethereum message that first goes to the registry. I'll talk in a bit later more about the registry. The registry recognizes that the recipient of the message is an EVM address 0. So it means that this is a contract creation transaction. So the registry first creates a temporary state that receives any state updates created by the EVM contract constructor. So for instance, contract constructors in EVM can set who's the owner of a coin and things like that. And also they return the eventual bytecode that becomes the contract bytecode. So it essentially executes the init code that is in the input field of the RLP message. Then when we have the resulting bytecode and the temporary state constructed from running the constructor, we couple them together and we create an instance of the EVM runtime by pointing to the EVM runtime CID and that state root. When all these pieces are ready, I mean, the instance gets its own address and it becomes a native actor that runs bytecode stored in its state. Let me now walk you through in contract invocation. And here I'll talk a little bit more about the registry. So on the left, you have an RLP message that is sent to the registry. The registry right now is a temporary component. We hope to get rid of it with the universal addressing, but for the purpose of this prototype and to make this whole thing work, we have this registry. It translates between Falcon addresses and EVM addresses. So the registry unpacks the RLP message and looks up the sender's EVM address. Once it finds it out, it resolves it to the native actor address that was created in the previous step, and forwards the RLP message to that address. The EVM, the native actor instance that has the bytecode for that contract living at that address interprets the RLP message and executes it against the EVM bytecode stored in its state. The bytecode that was returned by the init code. And because the EVM actors run as native FVM contracts, they have full access to the FVM runtime. They can call other native actors, they can call other EVM actors or built-in actors. And now let's see all this in action.
Exciting.
Yeah, here's some terminal. Okay, can you see my terminal? All right.
We can, yes.
Sure. Okay, cool. So we are going to run this Solidity code inside FVM. This Solidity code has a constructor logic that sets the balance of the creator to 10,000. It has storage here as a form of mapping and has functions that you can call. So if we invoke, run an integration test and actually test this code path, I'll walk you through the outputs of this. And you can see the previous slides in the logs of how they actually happen. So yeah, here we have an Ethereum transaction. The input value is the output of Solidity's compiler. So this is essentially the simple coin contract compiled to EVM bytecode. This bytecode, like I mentioned earlier, it sets the sender's balance to 1,000. So Solidity has this logic of how mappings work and how they're addressed. So it essentially executes the bytecode and in a temporary state sets that value to 1,000 and then returns the eventual, the final bytecode that becomes immutable when this thing is persisted. So here we get inside the new instance of an EVM runtime. And here you have the bytecode, here you have the initial state. This initial state is essentially a state through, it's essentially a hint that contains key value pairs because all state and Ethereum contracts are U256 mapped to U256. And also it keeps track of a couple of values here that are used for bookkeeping, like, what is the address of the registry and what is my own Ethereum address and so on. And here in the next step, we are invoking the same contract that was deployed here with the Solidity calling convention. So the first 4 bytes are the hash of the signature, and then we have the sender's address. And this is your typical RLP transaction that probably produced by MetaMask. And you can see here that the bytecode is getting executed and all these steps for the bytecode execution are printed out here. So it's reading the mapping entry for that particular address, and it's returning 10,000 in hex. So here the balance output is 10,000. So yeah, this is EVM on FVM. Now back to Raul.
That's awesome. Thanks a lot for that demo and that walkthrough. That was very cool. Awesome. I'm going to share my screen again and we'll wrap this up. All right. So we've walked you through M1, everything that went into M1. It's going live in less than 48 hours, and mainnet, fingers crossed, everything will be great. Then I also talked about M2, and I talked about M2.1 being EVM compatibility. This is our immediate focus here at the core team, at the FVM core team. Prior to M2.1, there will be another network upgrade, very likely. That's network version 17, that will be shipping programmability improvements ahead of time before we enable programmability so that developers can do useful stuff, more useful than what they can do today. What's important is that EVM smart contracts will be able to interact with built-in actors, and will be investing in the tooling to make that possible in the most frictionless way possible, which is likely a Solidity library, and maybe using some precompiles to access certain features of Filecoin if needed. And finally, this is going to be followed by M2.2, which revolves around WASM actors. And this will be able, basically the goal there is we'll be able to achieve better gas performance than EVM. So ideally you'd onboard potentially contracts that exist on the Ethereum community onto the Filecoin network, have them work there, and eventually if if you deem them to be successful and you want to decrease gas costs so that they receive more usage and traction, then eventually you probably want to migrate them to WASM actors directly. Now, what's next for the community? So I just talked about kind of like the roadmap key takeaways, and I want to like put some stuff out there as well for what you should expect as the community. First of all, we're going to be opening a new early builders cohort that is going to be focused on EVM use cases. So the existing cohort that's currently running is focused on native actor tooling. This new cohort is going to be focused on building use cases using the EVM. So if you're a builder, if you're interested in getting your hands dirty with all of this as soon as possible, then watch out for those comms and stay tuned and make sure that you apply as soon as they go out. If you want to stay updated with everything that's happening within the development activity of the FVM, then make sure that you subscribe to FVM specs, to the FIPS repo, and to Ref FVM, and generally all these repos, and watch things fly by, engage in conversation, ask questions, be curious about stuff. We're very happy to engage with everybody and clarify stuff and take all feedback into account. And finally, if you're interested in building with us, there will be a number of upcoming RFPs that we're planning. So make sure that you stay tuned for those. Things like Solidity libraries and precompiles for interfacing with built-in actors, things like automated. One thing that I would love to do is take a bunch of existing Ethereum contracts, a bunch of transactions, and in an automated fashion, extract them from mainnet, from Ethereum's mainnet, and in an automated fashion, run them against the FVM to make sure that compatibility is even, right? So this is something that we might post an RFP for. Another thing that we might want to do is create registries, on-chain registries, so that actor developers or EVM smart contract developers can post their ABI interfaces on-chain directly, so that chain explorers can then provide introspection on these new messages that are going to be flying on the Filecoin mainnet. I think it's really important that we provide that introspection, and it would be great if we could do this in the chain itself. And finally, probably we're gonna put out an RFP for tooling compatibility testing to make sure that one of the key goals and the key design characteristics of EVM compatibility is to meet developers where they are right now, which means make their tools compatible with Filecoin with no changes needed, and possibly just like if necessary, in the worst case scenario, just by deploying some form of plugin, but definitely no forks or anything like that. So we want to make sure that everything is fully compatible, and we might open up an RFP for that. And also we're hiring across the board in terms of engineering talent, in terms of product talent, in terms of developer relationships, developer relations. So if you're interested in working in this team and working to build the FVM together and to deploy the FVM together, then make sure that you reach out. Thank you so much. I don't know if we have time for questions and answers or the infrastructure for those. But if we do, then now is the time.
The question was, how is consensus achieved for the EVM smart contracts inside of FVM?
Oh, that's a great question. So we don't run any parallel consensus at all. You can think of the EVM runtime as basically being a state transition function, just another one that applies on the storage of the contract, that applies on the receipts and everything that and the logs that are produced. So basically all the side effects that an Ethereum contract, smart contract does are performed via opcodes and via receipts, essentially receipts that are emitted. So basically there is no parallel consensus like that. So in that sense, there is we don't actually arrive to consensus. I think we don't arrive to consensus on the receipts either, because the receipts are an on-chain thing. So it's basically we arrive to consensus on the return value, I think, and potentially some gas usage. But maybe Kareem can clarify here if you have something to add there.
Sure. Actually, we might be arriving to consensus on the logs bloom. So if all the logs, they all have to return the same thing. So, but I mean, I don't think that you can't think about native actors consensus and Ethereum actors consensus as two different things, because an Ethereum contract is essentially a native contract. It's a special case of a native contract where one of its state component is the EVM bytecode, and the WASM bytecode essentially is an EVM interpreter and execution like a engine. So I mean, conceptually, it's not very much different than a JSON parser, really, but it's just that it's compatible with the EVM bytecode. So whatever consensus we use to arrive at the same state transition for native actors applies to EVM as well.
Yeah, which is using Filecoin consensus under the hood. So all of the security power of
Exactly.
The Filecoin storage providers that are providing consensus in Filecoin is now also providing consensus over these Ethereum smart contracts running inside of FVM. Tell me if I'm saying that wrong, but.
That's correct. That's correct. Yeah, we use Filecoin consensus, and yes, EVM contract execution is an execution, basically an execution thing. It doesn't affect consensus.
Other folks have questions?
So yeah, we are building like a project sort of using EVM and Filecoin. This is very interesting. I remember when I first pitched this, FVM was supposed to sort of solve it. So I'm trying to understand like how much data are we able to push? So for example, let's take an example of an ERC20 transfer event, right? So how much can we push? Because technically there's no limitation, right, on the Filecoin side in terms of data storage. But because like I was curious about the consensus answer to like trying to understand as a developer, like how much can we push and what is like a throughput, or is there any limitations? Obviously, we can't compare it to Ethereum directly, but on your side.
Right. So I think it's important to differentiate between data that is stored on the Filecoin network and the chain and state data. From what you're saying, it sounds like you're talking about state data. And basically your limit here is your gas limits and how much you're willing to spend on the transaction itself in terms of monetary, payment for that transaction when it comes to the base fee and the gas usage of that particular storage of data, or that emission of data in the form of a return value or a log or whatever, a transfer event as such. It just applies. If you're talking about state, it's throttled by the gas and how much gas you're willing to spend.
Raul, is there an option of doing kind of you have something in state and then you push it to Filecoin storage for like longer term persistence where it's no longer in state and you don't have to pay for gas for it?
Yeah, so you can imagine, for example, creating some form of a blob that that storage providers could then provide a service of storing somewhere else and then proving to the network that they've done so. However, this is like a specific interaction from and likely performed by kind of like a layer 2 network that anchors and runs on top of the Filecoin chain that is providing this offloading feature set of data onto the storage network of Filecoin, and then ultimately proving to the contract that they did the job. So like these two things are dissociated from the state. From contract execution, you'll be able to query the state of a particular sector, particular deal. You'll be able to interact with the proving facilities of the network, essentially. But when it comes to the storage, you'll likely need, like we're looking for, one of the prime use cases that I want to see developed as soon as possible is precisely that, the facility to offboard data into Filecoin storage and then prove to contracts that it's been done.
On Ethereum, you have a limit of 24 kilobytes for smart contracts. Is the same limit present on FVM?
Where in principle, technically speaking, no, but there is no reason from our opinion to increase it. That's what my argument would be, but I'm curious to hear what Kareem thinks as well.
Yeah, that's correct. Technically, our limit is Filecoin's limit. But if we look at Solidity's code corpus, usually those contracts don't exceed the 24 kilobytes. So technically speaking, there is nothing stopping us to use the entire Filecoin limit. Yeah.
I do want to add there, sorry, I don't know if there's a next question, but I do want to add there that some of the implicit limits that exist in the Filecoin network are around the maximum size of a message in the mempool. On the mempool, the bit swap size as well, and a bunch of like other things that stack together. The limit that is in force is the strictest one, which is 64K. That is the maximum size of a message in the mempool. Any message above that limit will be immediately rejected by the client. So we could technically expand up to that limit. I tell you that WASM actors in the future will go above this limit, and the technique that we'll be using, likely using there, or that we're thinking of introducing, is a concept of a bootloader actor. So basically, you have an actor that is to which you send multiple messages to create, ultimately to accumulate in state the code that it will ultimately use for the construction of the actor. So if you have an actor that is 1 megabyte large, for example, you would be sending multiple 64K messages, compiling that in state, and then ultimately just deploying the actor, which would deploy the actor from the state and then self-destruct that bootloader actor. And like we want this eventual feature would be in user space so that you can do things like not just the naive concatenation of bytecode, but things like, for example, patching of existing actors. So you can imagine an actor that is a patching actor that fetches bytecode of another actor, applies a patch, and then deploys that code, or actors that are applying some form of compression, right, or decompression. So like, you know, we want to put that innovation eventually into user land by making the bootloading element actually something that's in configure that developers can develop and deploy by themselves. But that's M2.2.
The question is the storage provider services, so proving capacity and performing storage deals and all of that, is that separable from the FVM and the compute, or I guess the smart contracts space? Are these two separate things that you can choose to participate in one or the other, or are they inextricably linked from each other and you must participate in both?
That's a great question. It ultimately depends on the application and the design of the application that gets deployed, right? So you can imagine that, for example, a network that is an application that is ultimately acting as a retrievability proving thing, right? A retrievability proving network would be potentially a layer 2 network whose nodes are committing onto the L1, which would be the Filecoin chain, committing proofs of misbehavior, for example. So for example, a storage provider that refuses to serve data given a well-formed request and the funds to do that, for example, right? If you have a proof of that, then eventually you would be able to post it on chain. So ultimately, like how these contracts interact with the built-in features will depend ultimately on the thing that's being built. So yes, you could create networks where you don't have to be, where obviously anybody can participate without being a storage miner, and that could be a retrieval network, right? So you can imagine, for example, retrieval nodes that are requesting data and caching data that is locally, hot in whatever, local means for them. It could be geographically, it could be latency based or whatever. And they're not a storage provider, but they're fetching that data and they're providing a service to the network, which is the caching of that data and that transitive serving of that data. And they're proving to the network to claim incentives that they are doing this job, right? So that would be an example, for example, a node a new economy that emerged on the Filecoin network that has nothing to do with storage providing, that is not coupled to the storage provider feature, right? But it ultimately is storage related.
And right now, Raul, since FVM is part of Filecoin state, the state of FVM is being, the consensus algorithm is being run by storage provider nodes over capacity stored in Filecoin, right? So at least for the layer 1 here, if you're a storage provider node, you will be running the state of the network, and FVM is now 172 happens. I guess actually 171 happens, is a part of the state of the Filecoin network.
Exactly, correct. Yeah, that's correct. And basically the Filecoin chain is validated through expected consensus, and this relates to the power accounting of storage providers. So they are ultimately validating the transactions, just like it happens today. However, there is also, so one of the endeavors that the FVM team is looking at doing at some point in the future is this decoupling of what makes an abstract execution environment inside FVM to kind of extract, many of these kind of like architectural decisions that we've made into a framework that can then be can be used to create other execution environments for things like, for example, compute over data networks, for things like maybe shard consensus and hierarchical consensus, trimmed down, like, specific networks, maybe inside IPFS and IPLD codecs, stuff like that, that could ultimately be using the same design as the FVM, but just the same substrate, if you want to, like the same foundation, so to speak, but with different syscalls, with different metering that does not use gas, that like uses some form of throttling, that uses some form of resource accounting or whatever. Like there's a bunch of possibilities there. We're affectionately naming that project, terming that project Interplanetary VM, but this is kind of like just, you know, vision for the future. But you can imagine in the future having new different networks that are anchoring and committing, L2 networks, for example, that are anchoring and committing to Filecoin's L1, using a different execution environment that has also been built on top of like this common foundation of the FVM. So it could be running the FVM, they could be running a different flavor of the FVM, right? But ultimately committing and proving to the Filecoin network and to a commitment contract that they're doing the right thing.
Jennifer wants to add on to what you said, but this is our last question.
Okay.
It's not like a question, but in general, so Consensus Lab, as like Protocol Labs, they're actually looking into kind of like sharding for the Filecoin network. It's called HC project, like hierarchical consensus project. So in the subchain, the idea is users can deploy their own consensus or their own smart contract to identify like how the consensus should be reaching in that like sub network. So it doesn't have to be the power actor or the manual power anymore. So I know the Consensus Lab is actually looking into the use case to be our first like subnet of like FVM M2. If you have any idea what that use case should be, you can join the Filecoin Slack consensus channel and like provide ideas. So I think a lot of computer over data like ideas can be reaching there. So it can be a part of layer 1 of Filecoin network instead of just like layer 2 application on top of FVM.
Yeah, if you're not already a part of the Filecoin Slack, it is an open Slack workspace where all of this work is happening. So join the FVM channel. There's an early builders program channel. There's a consensus channel. There's a compute over data channel. So please join the Filecoin Slack and you can chat with all of us there. But yeah, we'll pass it off to your next speaker. Thank you so much, Raul and Kareem, for this amazing presentation.